All right, let's go over the Bonding 5 MO Yo worksheet. This is a great review for any of the types of questions that you could be seeing on a test from me. We're dealing with bimolecular ions or compounds, and we're going to put them together. So let's do that. Let me choose a nice color. Let's go with gray. All right. Yeah, of course, it's not really a color, but hey, I'm tall. So we're dealing with the MO diagram of O2 plus. So this is basically oxygen bonded to oxygen, and of course the whole ion or this whole chemical species is +1. Okay, so when we think about these MO diagrams, think of the left-hand side. Okay, if I was to draw, a dotted line here, as the atomic orbitals. All right, the atomic orbitals. And of course, the right-hand side as the atomic orbitals of the other oxygen. So we've got an oxygen here, and you got an oxygen here, and they're going to come together, and they're going to form molecular orbitals. Okay. Now, before we do so, let's write the formula, or let's write the configuration. Oxygen is 1s2, 2s2, 2p4. And the other oxygen, we'll put as another color, what the heck, is 1s2, 2s2, 2p4 as well. Now, as we remember, we're trying to do this for O2 positive 1. Kind of a weird scenario, but we can do this easy with these types of molecular orbital diagrams. So for positive 1, that means we have one less electron. Now, I don't know which one it is, but one of these two oxygens, we're going to take off an electron. So I'll just do it here. So this will be 2p3. Okay? Okay. Now the first thing I'm going to do is I'm not going to consider the core electrons. Okay? Now the core electrons, you can say undergo MO diagramming as well. Okay? And of course they would cancel out for reasons we keep showing you. But we're going to deal just a valence shell. Okay? So any case. So the first thing I'm going to do is take my 2s electrons, and there's two of them. And I'm just going to put them here to show that, hey, I have them. And I have 2s electrons from this oxygen. Okay, remember, two oxygens are coming together. So we put the electrons in. We have 3 electrons, so 1, 2, and 3. And then this one, I guess I should be using black. I have 4 electrons. So I go 1 using Hud's rule, 2, and then of course, one more is going to have to pair up in one of the orbitals, and that's what I have. And that's what we're starting with. So these electrons here are what the atoms, the atomic orbitals have. Now we're going to put them together. So basically, these two, so we get, and I'm going to have to use different color, I guess. So I'm going to have one electron from that 2s come here, and another electron come from here, and that's going to be filled. Now there's 4 electrons from 2s orbitals. 2 electrons are going to make this sigma 2s orbital, this cylindrical, very stable bonding orbital, that due to waves constructively interfering. And then we're going to make this little star here, 2s sigma anti-bonding. And so 1 electron each went there, so the other electron is going to go here. So each one grabs 1. So 4 electrons come in, 4 electrons are in molecular orbitals, 1 each goes to the molecular, I would say the bonding orbital, and 2 go into the anti-bonding, which is the destructive interference. Okay, so we're done with the 2s. So now we'll do with the 2p3. So overall, I don't care how you do this, but there's an overall 7 of these electrons. Okay, 3 plus 4. So if I want to put all these in, so 1, 2, 3, that's filled. And now let's deal with the other 4. Remember, there's 1 less electron on this side because we're making this O positive type of ion. So I'm going to put the blacks in one at a time. 1, 2, 3, and then we have 1 more. I'm forced to go into the next lowest energy level, which overall is highest than everything else, which is this one. It's a pi 2p pi anti-bonding orbital. Okay, and that's all I did is I figured out my outermost valence electrons, and I put them in to the individual atomic orbital places. I made adjustments according to the electrons based upon the charge. This was O2 positive, so one of these two had to lose an electron. I made this side lose one. You could have easily been this one, and this one have 4. It would not matter, and you get the same diagram in the middle. That's what we're after. Now, what's the diagram in the middle tell me? Well, it tells me a couple different things. That O positive 2 has a particular bond order. Now, a bond order is going to be what the number of bonds we have left after we consider antibonding electrons. So we can see that we have antibonding electrons. The way to do this is you take all of your bonding electrons, and right here is a bonding, 1, 2. Here's another, 2p, 3, 4, 5, 6, 7, 8. I have 8 bonding electrons. We're going to divide by 2 because a bond is actually made from 2 electrons. And then I'm going to subtract the antibonding electrons, which is 1, 2, 3. And of course, divide that by 2. Okay, again, divided by 2 because a bond is a pair of electrons. Now, why am I subtracting the antibonding electrons? Well, I know that antibonding electrons destabilize and break a bonding orbital. So these 2 electrons in this antibonding orbital, because of destructive interference, destroys this bond here. Okay, so I know I wipe away 1 for 1 here, but thinking about this in terms of our diagram and using this formula, bonding electrons divided by 2 divided by the antibonding electrons divided by 2, and what I get is 4, 8 divided by 2, minus 1.5, and what we get is what? 2.5. So what does that mean? O2 has 2.5 bonds, so to speak, okay? And that's the bond order for O2 positive. It lost an electron. So if you think about it, maybe, okay, losing an electron creates that scenario. All right. What I like to do is take these bonding electrons and this anti-bonding right here, and notice that this is going to wipe out this bond. And then I have 3 bonds here. How do I know? Each filled pair is a bond. There's 3 bonding orbitals filled. It's 3 bonds. And then what am I doing? I'm subtracting a half a bond, right? Half of a filled bonding orbital, anti-bonding orbital will take away one of these electrons. All right, so we're going to destabilize half of a bond. So that starts out with 3, and then I'm subtracting what? 0.5 of a bond. Okay, and that gives me my 2.5 as well. I don't care how you think about it. But it's a nice little system to come up with a value of bond order. It tells me something about stability, bond lengths, and even bond energies. So predict the following properties. Number of unpaired electrons. Well, based on this, we're going to have 1 unpaired. And of course, that 1 unpaired is going to be in the what? Pi antibonding 2p orbital. Okay, the bond order. Well, we just got that as to be 2.5. Now, bond enthalpy is just bond energy, which means is the energy to do what? Break the bonds. In one of our lectures from MIT, we did this internuclear distance type of graph, and we noticed that this was the average bond length, and this was 2 hydrogen atoms. So the energy needed to go from this stable low energy position, this is energy, to here is our bond energy. That's how much energy we'd have to add, okay, to this stable position to break the bonds. Okay, now what do we know? Well, predict the following. Well, the bond length I'm going to say is going to be short. Okay, 2.5 bonds means that the 2 atoms are going to pull each other in pretty close. So we're going to say short. Now, normally I'm going to ask you to compare this to something else. The bond enthalpy we'll say is basically high. Now, why would I say high? Well, if they're pulled in tighter because they have more bonds between them, they're shorter. And if they're pulled in tighter, that means they're even more stable. If you have 2.5 bonds, that's a lot of bonds, it's going to take a lot more energy. So if this is a single bonded hydrogen here, something that's double bonded would be actually lower to show that it's what? More stable. So things that have multiple bonds, in this case more than 2 or 2.5 in this case, this is going to be a deeper little curve, and therefore it's going to be what? A lot more energy to break. All right. So we'll say a very high, so what you should know is that if your BO is high, okay, and that sounds like a personal problem, but if your bond order is high, okay, your bond length has to be short. That means if you're attracting a lot of electrons between two nuclei, they're going to pull themselves inward to each other. And because of the multiple bonds, the energy needed to break those bonds is going to be much higher. Okay? Moving on to the back side. All right, so the back side, I've got no diagrams here. So I'm actually asking you to draw them. And so what we're going to do is we're going to compare O2 -2 and C2 -2 to see if, in fact, what their bond orders are. And we could also make some statements regarding their bond length and bond energy. Okay, so I'm going to bring a carbon here. There's another carbon here. And what do we know about carbon? Carbon is 1s2, 2s2, 2p2. Now, if it's, I'm going to do carbon first. If it's -2, that means there is what? 2 extra electrons here. So this carbon is 1s2, 2s2, 2p2. What we're going to do here is we're going to add an extra electron to each of these. Now, could I make this 2 and the other one have 4? Doesn't matter as long as I add 2 electrons to this. Okay, so what are we going to do here is we're not going to consider the core electrons. We'll just do the outermost. So what we're going to start with is our 2 s's. Okay, so I'm going to make this my 2s electrons, and this is my 2s electrons. Remember, there's 2 different carbons coming together. And what do I have? I have 2 electrons in each of them. All right, so I can color code these. This will be black, and we'll make this one red. Now, what's going to happen, party people, is that we're going to create 2 new orbitals when they bond. We're going to create a bonding orbital. We're going to call this 1s sigma, and then we're going to create an anti-bonding orbital. And if you need to look at the other page or other examples to do this, we'll call this 1s sigma star. This is the anti-bonding. I should say 2s, sorry. My bad. Okay, now we're going to put electron from each, so let's do that. Here goes 1 electron. Here comes the other one. I'm just putting them together. This red came down here. Notice there's 2 left. So the other one would go into the 2s anti-bonding. And we can see that's probably going to cancel out, definitely. So what do I have left, party people? Well, I have, okay, 2p3. Now when I draw this one, okay, this will be 2p. And remember, there are 3 orbitals. And this will be 2p for the other carbon. And these are atomic orbitals. Now what's going to happen, okay, is that we're going to make 2 boxes down here. And these are called 2 pi. All right. And what we're going to have is we're going to have its anti-bonding orbital, and then we're going to have its anti-bonding orbitals. And that would be 2 pi star. And then we're going to have 2p sigma. And it's going to have its anti-bonding orbital, 2p sigma star. Okay? And again, you'll know it won't have to do this, but it's good to draw it to see what's going on. So let's put in the 3 electrons. We have 1, 2, and 3. Okay, and put the 3 electrons here. So it's 6 electrons overall. I guess I was supposed to color code this, bad Grotsky. So 1, 2, 3. And here comes the red. 1, 2, 3. So I'll put the reds in since I'm still red. 1, 2, 3, and do the black. Okay, and the black goes 1, opposite spins to fill. And I'm done. I have 6 electrons overall. And what does this give me? Predict the magnetic properties in bond order. Well, first of all, the magnetic properties, this guy is going to be dimagnetic. And the reason is there are no lone pairs of electrons in any of the orbitals, so all the opposite spins cancel out. And the bond order, well, quickly this anti-bonding is going to cancel this out, and there's nothing to cancel these 3, so the BO, okay, bond order is 3, okay? And that would be for C2 negative. Let's quickly try O2 negative 2. And I'll just do this on this side, okay? Now O2 negative 2, let's make some room here. We're going to deal with oxygen and another oxygen. And its configuration, I'll write over here, is 1s2, 2s2, 2p4. Okay, now this is O negative 2, so we're going to add electrons. This oxygen is 2p4 as well. So what we're going to do is put each of these oxygens coming together will be 2p5. So we're going to start with a 2s orbital. We're going to not talk about the inner 1s orbital. So this is going to represent 2s atomic orbitals. And of course, the first thing we're going to do is we're going to go to a lower energy state, a bonding orbital. This would be the 2s sigma. And of course, you can't help yourself, but you're going to also have destructive interference with the 2s sigma star, which is of course the anti-bonding. Put in the electrons. Okay, and I'm just going to put electrons in, not color code for this point. So both oxygens have 2s2. Remember, they're both oxygens. So one of each would go here, and the other 2 would fill the anti-bonding orbital. What's next is we have the 2 p's, right? So the p's, okay, I'll just draw 3 boxes here on one side and 3 boxes again. The things to the right and to the left are atomic orbitals. So we have, what did we say? We have 5 electrons, right? Because it should be 2p4, but each oxygen is bringing what? An extra electron. Again, I could miss and match, but total is 10 of these. So let's put in the electrons. This one has 5, so 1, 2, 3, 4, and 5. This is 1, 2, 3, 4, and 5. Okay, so let's draw our orbitals. Now, when we're at oxygen's level, these 2 energy levels switch. You don't have to know this, but I'm just for those that are trying to learn from this for another kind of course. The lowest energy level beyond oxygen, because of electron-electron repulsions, is going to be the 2p sigma in this case. So this will be 2p sigma. For my kids, we wouldn't have to know that. And of course, there's going to be an anti-bonding orbital up here, the highest, and that would be 2p sigma star. Then we're going to have some more bonding orbitals, 2 of them. And these would be 2 pi. And of course, you're going to have what? 2 pi star antibondings. Let's put in the electrons. And we're going to have, well, we have what? 5 altogether, so 10. I don't care who it is, but 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Each oxygen is 2p5 because of the extra electron. And so what do I have here? Well, the bond order for this, remember this is going to cancel this one. So this, and let's just write it here, this electrons will cancel these electrons, so you can wipe away that bond, and then these 2 bonds, these 2 anti-bonds will cancel this away. So what we have for O negative 2 is a bond order of 1. Now if you don't like what I just did, do what your teacher may have told you. The bond order is equal to the bonding electrons, 1, 2, 3, 4, 5, 6, 7, 8, divide by 2, which is 4, minus your anti-bond electrons, 1, 2, 3, 4, 5, 6. 6 divided by 2, each pair of electrons a bond. So you have 4 minus what? 3 gives you a bond order of 1. Okay? So all of these anti-bonding electrons destabilize most of them except for a bond. So there's one bond order. Okay? And this is also diamagnetic, and the reason is there's no lone pairs. Now here's what I could ask you is, which one of these two has a shorter bond length? Well, because C2, -2, has a bond order of 3, it's going to have what? A higher bond energy to break it if it has 2 more additional bonds, and it's going to have a shorter bond length because it's being pulled in tighter. So that's important you get that. So this one, okay, O-2 with a bond order of 1 is going to have a lower bond energy, a bigger bond length since it doesn't have a lot of electrons to pull, and of course a bond order of 1. So that's important to do. All right, and that's what I'm doing here. So the next one's very simple. Which one's expected to exist? Now that one we're going to do by the same reason. Now expected to exist would mean essentially who's got a bond order that's greater than 0. Okay, so let's do our neon. Here's my neon, here's another neon, and as we should know, neon is 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. So let's make this, again, we're getting rid of the 1s orbital. If you can figure out, they would actually cancel out as well. So this is my 2s orbital. This is my what? My antibonding sigma 2s orbital, and this, of course, is my what? My sigma 2s antibonding. Okay, what else am I going to have here, party people? Well, neon is a lot like my oxygen, so we're going to have the 2p sigma being lower. So we're going to have 2p sigma here, 2p sigma, and then we're going to have the 2 pi bonding, 2p pi. This is going to make an anti-bonding orbital up here, and this is going to make 2 anti-bonding orbitals up here. And of course, we have 3 atomic orbitals. My boxes stink. Okay, this of course is, these two are 2 pi star, and this right here is 2 sigma star. Okay, let's put in our electrons. Everything is filled, and we can see what's going to happen here. So we're going to fill this up, that's going to cancel, and we have what? 6 plus 6, 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you notice something, we have what? We have 3 anti-bonding orbitals filled, which will cancel these bonding orbitals, and we have 1 canceling this one. So the bond order will be 0 and N2 does not exist. Okay, now if I just go back and take off these, take this off, maybe, how do we expect N2 plus? We can use the same diagram and make some adjustments here. Now N2 plus would mean that we're going to take off an electron. And you probably can see this pretty quickly, what's this going to look like. So if I was to take off, okay, let's see if I pick white ink. Okay, so if I take off one of these electrons, so this, I'm choosing this one, but it could be any of them. So this, one of the 2 is missing an electron. That's why the whole thing is Ne+2. Ne2 plus, okay? So going back to that white ink, what's going to happen is there's going to be 1 less one here. So what's the bond order now? Okay, maybe some of you guys can see it, but how many bonding electrons do we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2 gives me 4. Subtract the antibonding. 1, 2, 3, 4, 5, 6, 7. 7 out of 2, okay, which is what? Okay, so we have 7 over 2, which is 3.5. So what does this give me? A 0.5 bond order. Well, it's greater than 0, so therefore it exists. Ne2+ exists. All right, hope that helped.